Hi, welcome back. This is Professor Ridge, and today's lesson is on section 8.1, Sequences and Series. An infinite sequence is a function having for its domain the set of positive integers 1, 2, 3, 4, 5. Notice 0 is not in there and the negative numbers aren't in there. So we want positive integers 1, 2, 3, 4, 5, so on. A finite sequence is a function having for its domain the set of positive integers 1, 2, 3, 4, 5, so on, up to some positive integer n. So we're going to stop at a positive integer. So finite meaning we're going to stop. Infinite sequence, we're going to go on forever. Okay, let's consider the sequence given by the formula a of n equals 3 to the n. So again, this is function notation. And here, we should be familiar with it, but we're restricting the domain to be just positive integers, so we can just put in 1, so 3 to the 1, which is just 3. A of 2 would be 3 squared, which is 9. A of 3 equals 3 cubed, which is 27. A of 4 is 3 to the 4th, which is 81. Okay, so this is should be pretty comfortable for you. You should have no problem. Now the idea is when we do sequences, we tend to not use the function notation. We use this notation here. A sub n is 3 to the n. So this is our sequence notation. Okay, so we might call the sequence A, and A with the subscript will tell you the first term. So A sub 1 is the first term of the sequence A, and then you use the same thing just like function notation. So it'll be 3 to the first, which is just 3. The second term, so A sub 2 would be 3 squared, which is 9. A sub 3, which is your third term of the sequence, would be 3 to the third, which is 27. And then the fourth term would be A sub 4, which is 3 to the fourth. Okay, so it's just a different notation, and it's the same idea, right? So just takes a little getting used to, but it's not anything that you're not capable of doing by now. Okay, so let's just kind of note the notation here. The first term is denoted A sub 1. Okay, so again, that's the first term. And the fifth term would be A sub 5. And the nth term, or sometimes we refer to it as the general term, or a general term of the sequence, is A sub n. Okay, so A sub n is just some general term for the sequence. Alright, so let's look at an example. In each of the following, the nth term, the general term, is given. Find the first 4 terms, A, and then we want to find A sub 10 and A sub 15, so the 10th term and the 15th term. So we want the first 4 terms, that's A sub 1, A sub 2, A sub 3, A sub 4. Then we also want to find the 10th term, so A sub 10, and the 15th term, A sub 15. Okay, so notice, it's just like function notation. The subscript is the number you're going to substitute in for n. So n's 1, so A sub 1 would be 1, 1 plus 1, which is 1 times 2, which is 2. A sub 2 would be 2 times 2 plus 1, which is 2 times 3, which is 6. A sub 3 would be 3. And if you notice the pattern, you don't have to keep plugging it in. 3 plus 1, so that would be 3 times 4, so this, which is 12. So basically it's going to be 4 times 4 plus 1 is 5. So 4 times 5 is 20. It's going to be 10. 10 plus 1 is 11. So that's 110. It's 15. 15 plus 1 is 16. And that's 240. Okay, let's try another one. So a sub n is negative 1 to the n minus 1 power times 4n minus 2. So we want to do a sub 1, a sub 2, a sub 3, a sub 4, a sub 10, a sub 15. We get negative 1 to the 1 minus 1. 4 times 1 minus 2, which is negative 1 to the 0 times 4 minus 2 is 2. Negative 1 to the 0 is positive 1 times 2 is positive 2. Then we're going to get negative 1 to the 2 minus 1 times 4 times 2 minus 2. That's negative 1 to the 1. 4 times 2 is 8 minus 2 is 6. Negative 1 to the 1 is negative, times 6 is negative 6. A sub 3 would be negative 1 to the 3 minus 1. 4 times 3 minus 2. So we get negative 1 squared times 12 minus 2 is 10, which is positive 1 times 10 is positive 10. A sub 4, so it's negative 1 to the 4 minus 1. 4 times 4 minus 2, so it's negative 1 cubed times 14, which is negative 14. And notice how our answers, we got positive 2, negative 6, positive 10, negative 4. What causes this is called an alternating sequence. So whenever you get a positive, negative, or the other way around, negative, positive, positive, that's an alternating sequence. And what causes that is the negative 1 to the n or negative 1 to the n minus 1. And that'll alternate between positive and negative. So that's the trick of how you get alternating positive, negative. It's the negative 1 to a power that makes it positive or negative. So 10 minus 1, 4 times 10 minus 2. So negative 1 to the 9 is negative 1. And then 40 minus 2 is 38. So that would be negative 1 times 38, which is negative 38. And then for the 15, negative 1 to the 15 minus 1 times 4 times 15 minus 2. So it's negative 1 to the 14 times 60 minus 2 is 58. So that is positive 1 times 58 is positive 58. Okay, so again, alternating sequence, the sign alternates between positive and negative. You're going to get negative 1 to the n is going to produce negative 1 to the 1 is going to get you negative 1, positive 1, negative 1. See, so this would be A1, A2, A3, A4. So negative 1 to the 4th power is positive 1. Negative 1 to the 5th power is negative 1. So it alternates positive, negative, positive, negative. If we did negative 1 to the n minus 1, now see that now 1 minus 1 is 0. So this will get us positive 1 for A sub 1. A sub 2 would be negative 1. A sub 3 would be positive 1. A sub 4 would be negative 1. A sub 5 would be positive 1. Because when you subtract 1, now it becomes an even number. Negative 1 to an even is positive. Okay, so just kind of keep that in mind. If you ever want to create an alternating sequence where the sign alternates, you put the negative 1 to the n or negative 1 to the n minus 1 in front of your expression, and that creates the positive negative signs that alternate. Okay, let's try now doing the other direction. Let's predict the general term of the sequence. I'm going to give you the sequence, and you're going to try to predict the general term. So if I gave you like 3, 9, 27, 81, 243, what would the next number be? If you can figure that out, and then you can figure out what the general term would be. So a sub n would be equal to what? And basically what I tell my students usually is, you just make a guess and, try simple things like, well, what can you do to 3 to get to 9? Well, let's see, you can add 6. Okay, so that if your prediction is going to be, you're going to add 6, you take, and then you're going to add 6 to 9, and you get 15, which then that doesn't work. So adding 6 is not correct. And then if you say, okay, well, 3 times 3 is 9. Now 9 times 3 is 27. 27 times 3 is 81. So when you repeatedly multiply by the same number, what if I do 3 times 3, that gets my 9, times the 3 gets the 27, times the 3 gets the 81. The shorthand for that is exponents. That's 3 to the 4th. So you can see now that to get 3, that's 3 to the 1st. To get 9, that's 3 to the 2nd. To get 27, it's 3 to the 3rd. So then our prediction is going to be a sub n is going to be 3 to the n. And then you just check to make sure it works for all the terms that you're given. So 3 to the 1st is 3, 3 to the 2nd is 9, 3 cubes 27, 3 to the 4th is 81, 3 to the 5th is 243. So it checks out, and we're going to be satisfied with that answer. All right, let's look at another one. So I have square root of 2, 2, square root of 6, 2 square root of 2, square root of 10. Now on this one, what I used to tell people is, first of all, what do you notice about most of these terms? And you should be saying, well, look, they all have a square root except the 2. So it's a lot of times when we're looking for patterns, it's best to make them all have the same thing. So simplified form sometimes conceals the pattern. So what you need to do is unsimplify it, put them all so they're all square roots and not simplified. So we got 2 square root of 4, square root of 6, 2 square root of 2 is square root of 8, square root of 10, and hopefully now you can see that the pattern, you got 2 times 1, 2 times 2, 2 times 3, 2 times 4, 2 times 5. And they're all on the square root, so that's going to get you 2n under the square root. So a sub n is 2 square root of 2n. Okay, so just basically you just guess something, try some easy stuff, see if it works, you check it for all of them. If that doesn't work, try something else. And it just takes some experience. You'll get better at it. And then, sometimes you give up and then you look at the answer in the back of the book and go, oh, yeah, that makes sense. And then you learn from that. Okay, so on to series. Given the infinite sequence, a sub 1, a sub 2, a sub 3, so on, a sub n, so on. So basically you're just given the infinite sequence. If we take the sum of the terms, so that's the key thing, the sum of the terms, a1 plus a2 plus a3 plus dot 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 plus a sub n plus dot dot dot. So if you add them all up, that's what's called an infinite series. So infinite series is a sum of all the terms of an infinite sequence. Nothing fancy there. We're just giving a name for, if we take all the terms of a sequence, add them together, that is called a series. Okay, so now a partial sum is the sum of the first n terms. So maybe we don't want to add them all up, we just want to add up the first 10 terms, or the first 3 terms, or the first however many terms, right? So that's, we'll say a sub n for whatever number we want. Okay, so if we want to add up the first n terms, that's called a partial sum. It's also called a finite series, or the nth partial sum, and is denoted S sub n. So we're going to use a capital S for series. So generally for sequences, we'll use A sub 1 as the first term, sequence A. Now if I'm going to add up the first 5 terms, I'm going to do S sub 5. That's going to be the sum, partial sum, of the first 5 terms. Okay, so again, that's notation. Okay, so we got a sequence 3, 7, 11, 15, 19, 23, 27, so on. We want to find S sub 2. So that's the partial sum of the first 2 terms. So it'll be 3 plus 7, which is 10. So S sub 2 is 10. Partial sum of the first 2 terms is 10. Now S sub 5 would be S sub 1, A sub 1 plus A sub 2 plus A sub 3 plus A sub 4 up to A sub 5, the 5th term. So we're going to get 3 plus 7 plus 11, 15 plus 19, which equals 55. Now let's try one more. So 1, negative 3, 5, negative 7, 9, 11. Find the partial sum of the first 3 terms. So S sub 3 is 1 plus negative 3 plus 5, which gives us 3. And then the partial sum for the first 6 terms would be 1 plus negative 3 plus 5 plus negative 7 plus 9 plus negative 10, or negative 11, which gives us negative 6. Okay, now let's move on to sigma notation. Okay, so sigma notation or summation notation. So really it's summation notation, but since we use the Greek letter sigma to signify it, a lot of people call it sigma notation, which is fine. And so the way it works is we use the Greek letter sigma, and then if I have the nth term is given as 2k plus 1, and k is what's called the indexing variable, and we're going to start plugging in k equals 4, then you're going to index the variable, meaning you're going to add 1 to it, and plug in 5 now for k. So 2 times 5 plus 1, index the variable. So now we're at 6. So 2 times 6 plus 1, then we're going to index the variable and go to 7. 2 times 7 plus 1, index it to 8. Now we're going to go to 9, and then the number on top of the sigma is your terminal number. So we're going to stop at 9. So we're going to start at 4, and then we're going to index 4 to 5 to 6 to 7, and we're going to stop at 9. Okay, so we're going to start at 4, and we're going to end at 9. And then again, k is your indexing variable. Alright, so we're going to get 8 plus 1 is 9, 10 plus 1 is 11, 12, 13, 15, 17, 19, add all those up, and we get 84. Alright, find and evaluate the sum. So we got the, again, you can say sigma or summation. We got the summation of I times I plus 1, where I goes from 1 to 10. So that's the way you read it. Let me say it again. So we got the summation of I times I plus 1 times the quantity I plus 1 from I equals 1 to 10. So again, we're going to take our indexing variables I, so everywhere I see an I, I'm going to put in 1 for I, and then I'm going to index it. Now I go to 2, so everywhere I see I, now I'm going to put in a 2. So 2 plus 1, index it. 3, 3 plus 1, index it. 4, 4 plus 1, 5, 5 plus 1, 6, 6 plus 1. Okay, so I got the idea, right? So it's 6. Now we're going to go 7. 7 plus 1 is 8. 8, 8 plus 1 is 9. 9, 9 plus 1 is 10. And then we're going to stop at 10. 10 plus 1 is 11. So we got 1 times 2 plus 2 times 3, 3 times 4, 4 times 5, 5 times 6, 6 times 7, 7 times 8, 8 times 9, 9 times 10, 10 times 11. Hopefully you can see that. So you got 2 plus 6 plus 12 plus 20 plus 30 plus 42 plus 56 plus 72 plus 90 plus 110. Punch that all in your calculator and you should get 440. Okay, so summation of kx, where k goes from 1 to 4. So we're going to start with 1 for k. X just stays x. So we're just indexing k. Starting at 1, index it, goes to 2, 3, then 4. So 1x plus 2x plus 3x plus 4x, which equals 10x. As simple as that. All right, let's go the other direction. Write sigma notation. So basically, it's just like if I were to ask you, what's the nth term? Think of it that way. Plus dot, dot, dot. So if I asked you, hey, what's a sub n? And you were to figure out, let's see, that's 7 plus 7, or 7 times 1, 7 times 2, 7 times 3. Now the thing is, if you added, we're adding 7, added 7, so if we add 7 repeatedly, right, add 7, add 7, add 7, add 7, that tells you it's 7 times. Okay, and it's 7 times 1, 7 times 2, 7 times 3, 7 times 4, 7 times 5, so that's 7n. Now when we do the summation notation, pick a letter for your indexing variable, not n, something else. Let's say we can use I, J, or K as pretty standard. So we'll use I, equals 1, and we're going to go 7, and now instead of using n, we're going to use our index variable, which is I. So 7 times 1, 7 times 2 would be 14, 7 times 3 would be 21, so on. And we're going to go from 1 to, now this one doesn't stop, it goes forever. So we just put the infinity symbol on top, meaning we're not going to stop. So it'll be 7 plus 14 plus 21 plus 28, so on, forever. Okay, let's try another one. So we got 1 over 1 to the first, no, squared, sorry. 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared. And this stops. So, and you should be pretty easy to recognize the pattern here. You got 1, 2, 3, 4, 5, and all those are being squared. So the thing that's staying the same is 1 over some number squared, and let's use k this time. So it's going to be 1 over k squared, and we're going to start at 1 and end at 5. So that's your answer there. Okay, and again, a lot of this just takes some practice, and you'll get better as you do more examples. Alright, and then the last thing in this section is to talk about assigning sequences defined recursively. A sequence may be defined recursively, so this is a new word, or by using a recursion formula. Okay, such a definition lists the first term, or the first few terms, and then describes how to get the remaining terms from the given terms. So basically we're going to describe what do you do to a term to get the next term, or what do you do to the first two terms to get the third term, or whatever. Okay, so we're going to give you a description of how you find terms based on previous terms. Okay, so we have to start the chain, and then we'll go through the motions here. All right, let me give you an example. Okay, so if I give you a sub 1, okay, find the first 5 terms sequence. And we're going to do this recursively. So if I give you the first term is 3, and then given, if you want to find if you know a term, just add 5 to it, and that gets you the next term. That's kind of the way you read this. So what I do is, so to find a sub 2 is going to be a sub 1, so the term before it, plus 5. So that's going to be, and then to get a sub 3, I need to know a sub 2 plus 5. And a sub 4 is going to be a sub 3 plus 5. So you've got to take the term before it and add 5. And then a sub 5 would be a sub 4 plus 5. So we can't do any of these until we know a sub 1, which I told you was 3. So 3 plus 5 is 8. And now I can do a sub 3, because now I know a sub 2 is 8. 8 plus 5 is 13. And I can do a sub 4. So 13 plus 5 is 18. And then a sub 5 would be 18 plus 5, which is 23. Okay, so that's defining it recursively. Now I can give you 2 terms, like a sub 1 is, say, negative 10. Well, let's just do positive 10. And a sub 2 is, say, 4. And then a sub n plus 1 is a sub n minus a sub n minus 1. Okay, so to find the term, you got to take the term that's right before it minus the term before that one. So a sub 3 is going to be a sub 2 minus a sub 1, which is going to be, now be careful, 4 minus 10, which is negative 6. And a sub 4 is a sub 3 minus a sub 2. A sub 3 is negative 6 minus a sub 2 is 4. So I guess that's negative 10. And a sub 5 would be a sub 4 minus a sub 3. A sub 4 is negative 10 minus a negative 6. So that'd be 10, negative 4. Alright? So that's defining a sequence recursively. That's how you do it. So you describe what you do to get a term, you got to describe what you do to the preceding terms to get the next one. Alright, so that concludes the lesson for 8.1. Go to My Math Lab, complete your exercise there, and I'll see you next time.